Right now, at this very moment, something might be passing through you. And it's okay. Just breathe. It's not radiation, not in the way we usually think of it, not gravity, not the kind we're familiar with, not anything with a name, not anything you'd find in any textbook, on any shelf, anywhere in the world. It's something that interacts so gently, so selectively, so quietly, with ordinary matter that every single atom in your body feels absolutely nothing. No warmth, no pressure, no tug, no push, nothing at all. Not a ghost. Ghosts at least make the hair on your neck stand up. But this would pass straight through you with such soft indifference that all the trillions of atoms in your body would notice it the same way they notice an idea passing through your mind. Not at all. The only reason physicists even think this thing might be real is because a tiny particle, smaller than anything you can truly imagine, a particle that exists for less than 2/millionths of a second before fading away, wobbled. Just a wobble, inside a magnetic ring in the quiet Illinois countryside. A wobble that was just a little too much. One tiny wobble. A discrepancy tucked deep into the 8th decimal place of a calculation. A number so small, so hidden, that you'd need years and years of physics just to understand why anyone would care about it. And yet, they cared. Deeply. Because in their world, something that small isn't a mistake. It isn't a glitch. It isn't noise. In the world of precision physics, a deviation like that is a rupture. This is the story of that rupture, and it's all right, take a breath. Because we're going to move through it gently. This is the story of what might be the very first fingerprint of a force reaching out, connecting our visible world, this thin, fragile little 5% slice of reality we call the observable universe, to a hidden sector that makes up almost everything that has ever existed. Just get comfortable. It's okay. The closer you follow this story, the stranger it becomes. And we're going to follow it slowly, all the way to the edge. There is a version of this story where everything is fine, where physics behaved exactly the way it was supposed to, where the machines hummed along perfectly, where the numbers came back clean, where the greatest intellectual framework in the history of science held steady without even a tremor. That version is simpler, but it isn't the one we're going to tell. And that's okay. We'll take it one step at a time, because something happened. Something quiet, something careful and measured. It didn't come from a dramatic explosion in a lab, or a catastrophic equipment failure, or a sudden lightning bolt revelation. It came from a number, a tiny one, sitting way out in the 8th decimal place. And before we can understand why that mattered so deeply, we need to understand what was already standing when that number appeared. We need to understand what was at stake. The standard model of particle physics, and it's okay to pause here and breathe, is, in the truest and most honest sense, one of the greatest intellectual achievements in all of human history. Just imagine this with me for a moment. The standard model, it grew slowly, gently, over the 20th century, piece by piece, experiment by experiment, crisis by crisis. And then, the numbers stopped cooperating. I know that feels strange. To understand why, you have to know something about the way particle physicists live and breathe. This isn't a field where you see an anomaly, nod, and move on. No. When something doesn't match the prediction, they don't shrug. They investigate. Carefully. Patiently. They check the calculation. Then they check it again. They check the equipment. They look for anything that could interfere. Magnetic, thermal, electronic, computational. They run the analysis again and again and again. And when they've done everything they can, they hand it all to another team and quietly ask them to find the error. And that takes years, sometimes decades. Because in this world, announcing a false discovery, that used to be one of the worst things a scientist could do. So the standards are high, very high. A result has to reach something called 5 sigma before anyone will begin to believe it's real. 5 sigma means the chance it's just random noise, pretending to be a signal, is less than 1 in 3.5 million. Not 1 in 1,000, not 1 in 100,000, 1 in 3.5 million. It's okay. Take your time with that. It's a lot to take in. I'm right here. What we're talking about? It isn't fear. It isn't caution. It's something closer to a kind of earned, quiet wariness. The kind that comes from being hurt before. The history of this field is full of beautiful, promising results. 3 sigma whispers that sparked excitement, filled conference rooms, inspired theories, only to fade away into noise when better data arrived. And every one of those moments cost something. Time, trust, enormous effort pointed in the wrong direction. So this 5 sigma rule scientists cling to, it's like scar tissue. A memory of how badly we all want to find something new, and how easily that longing can bend what we think we're seeing. So when physicists at Fermilab and at CERN started noticing measurements that didn't quite match what the standard model promised, they didn't celebrate, they didn't rush to announce anything, they just sat down. And they looked for their own mistakes, gently, carefully. And what makes this whole story worth sitting with, worth the time we're giving it right now, is that they kept looking for years. And the strange little discrepancies, they kept surviving. Not clearly, not cleanly, but quietly, persistently, like a soft whisper from a place the standard model had never touched. And there's a question I want you to hold gently in your mind from here on. Could there be a force, a real, fundamental force of nature that slips through ordinary matter so completely, so selectively, that it is physically impossible for us to detect it? Slow down with me for a moment. Take a breath. What I'm about to tell you, it isn't caution. It's something closer to a quiet, earned wariness. Because this field, it carries scars. Decades of beautiful, thrilling 3 sigma signals that lit up conference halls, that sparked theories and hope, only to fade into nothing the moment better data arrived. And every one of those moments cost us something. Time, trust, whole paths of research drifting into dead ends. So that 5 sigma rule we talk about, it's not stubbornness. It's memory. It's the way a whole community reminds itself how much we want to discover something new, and how easily that wanting can bend what we think we see. So when the physicists at Fermilab and the ones at CERN began to notice little things that didn't quite match the standard model, they didn't celebrate. They didn't call the press. They didn't let themselves whisper the word discovery. They just sat down, quietly, carefully. And they looked for their own mistakes. And what makes this story worth holding gently in your mind is that they kept looking for years. And those strange little discrepancies, they didn't go away. Not clearly, not loudly, but persistently. Like a soft sound from somewhere the standard model had never reached. I want you to sit with a question now. Just hold it. Let it rest in the back of your mind. Could there be a force, a real fundamental force of nature that slips straight through ordinary matter so completely, so selectively, that we can never detect it directly? Not because we're not clever enough. Not because we need better tools. Just breathe with me for a moment, and let's walk through this gently. The G factor for an electron, or a muon, was once thought to be exactly 2, long before quantum mechanics had fully found its footing. But then quantum field theory arrived, soft and subtle, and it brought with it the idea of virtual particles, Tiny, flickering whispers in the vacuum, appearing and disappearing so quickly they almost feel like a thought or a dream. And those delicate little fluctuations, they nudge the muon just a bit, shifting its G factor away from that perfect 2. That tiny difference, the one between the actual value and 2 divided by 2, is what we call the anomalous magnetic moment, A sub B mu. And to understand it completely, you have to account for every quark, every boson, every fleeting interaction the muon might brush against during its brief existence. It's a lot, I know, but stay with me. The standard model can do this. And it doesn't just do it well, it does it with a precision that's honestly breathtaking. The predicted value and the measured value should match to better than 1 part in a million. Think about that, and let yourself appreciate how astonishing that is. A century of theory, all lining up that closely. But the Fermilab experiment wasn't searching for close enough. It was looking for the tiny space between extraordinary agreement and perfect agreement. And if that tiny space exists, that's where new physics might be hiding. And the experiment itself, it's worth picturing slowly. There's this superconducting magnetic storage ring, a perfect circle, with a diameter of roughly 15 meters, about 50 feet. This ring rests in a chill so deep, it's nearly absolute zero. And the magnetic field it creates, it's so steady, so carefully shaped. The scientists who built it whisper that it may be the most uniform magnetic field ever made by human hands. Not just for this kind of machine, but ever. Muons are created gently, by firing protons into a target, then choosing only the ones spinning just the right way, polarized, as they say. Those muons are guided into the ring, where they circle quietly, and the magnetic field makes their spin begin to precess, to wobble. And that soft little wobble, that's what the experiment listens for. All around the ring, thousands of detectors wait patiently, catching the tiny signs of muons fading away. From the pattern of those decays, the direction those electrons drift as the muon breaks apart, the physicists can pull out the precession frequency with such calm, extraordinary precision. Think of it like watching a spinning top on a table. Just take a moment with that image. If you tilt the table even just a little, the top begins to wobble gently around its own axis, in a way you can almost predict if you breathe and pay attention. And that wobble, it depends on what the top is made of. Its weight, its spin, its moment of inertia. Now, imagine that top is a muon. And the magnetic field, it's like that slightly tilted table. The wobble you see, that soft, steady motion, is the anomalous precession they're trying so carefully to measure. And if that wobble moves just a little faster, or a little slower than what the theory says it should, it means something quiet, something unseen, is touching it, something the theory didn't prepare for. The experiment first ran at Brookhaven, back in the early 2000s, and even then, it whispered that something was different. The measurement sat just a bit higher than what the standard model expected. It was intriguing, almost hopeful, but not enough. The uncertainty was still too large. It could have been nothing more than a statistical fluctuation. They needed something clearer, something steadier. So the decision was made to move the experiment to Fermilab, where the precision could be improved. But moving something like this, it isn't like moving a piece of furniture. It takes patience, care. The 50-foot superconducting magnetic ring had to be transported on a custom flatbed barge, and then carried on a specially designed vehicle, traveling more than 1,000 miles. Across rivers, along highways, through the night. It's all right, just breathe with me for a moment. The ring had to stay whole. You know, it was too delicate to take apart, too fragile to risk even the smallest touch. Its magnetic uniformity was extraordinary, and any attempt to break it down and rebuild it could have caused real harm. So they carried it, gently, patiently, all that way. It's okay. Just let the thoughts settle. That journey, it took 15 months of careful planning, and even a quiet nighttime convoy that, just for a moment, became its own little news story. Crowds gathered along the route just to watch. Local police departments worked together, gently coordinating traffic holds across multiple states. A piece of scientific equipment had become, briefly, a spectacle. And it arrived intact. The Fermilab run started collecting data in 2017, and in April of 2021, the first results were shared with the world. The measurement confirmed and even extended the discrepancy from Brookhaven. The combined results showed a difference between the measured value and the standard model prediction of about 2.4 parts per million. I know, that sounds like almost nothing. But in the world of precision physics, predictions are expected to be accurate to 1 part per million or better. 2.4 parts per million is actually very large. The statistical significance reached 4.2 sigma, so close to that 5 sigma discovery threshold, but not quite there. Still, close enough to be taken seriously. It was close enough to stir up this enormous excitement, and close enough to the threshold that every measurement afterward felt like holding your breath, waiting for some quiet verdict to arrive. And what made this little anomaly so intriguing wasn't just how big it was, but what it was. If the muon is wobbling faster than it should, then something gentle but real, is touching it. Something the standard model doesn't quite know how to hold. Virtual particles we already understand add to that wobble in careful, predictable ways. But an extra nudge from some unknown particle, some new boson, maybe even the whisper of a fifth force, would push that wobble exactly the way the experiment was seeing. And no, you can't look at this one number and know exactly who touched the muon. It doesn't leave a note. It just leaves a hint. A soft suggestion that something is there, something our theories haven't accounted for, something that brushes against muons in a way that shifts their spin just a little more than expected. And then, much later in the story, something changed. Not the experiment, the theory, the calculation. The universe stayed steady. But our map of it shifted beneath our feet. The muon's misbehavior, it wasn't a loud crash. No, it was more like a gentle drift. A soft, quiet departure from the path we expected it to follow. Measured over years, patiently, in a magnetic ring the size of a small house. The universe didn't shout. It didn't try to startle anyone. It just wobbled, ever so slightly, in the 8th decimal place, almost as if it were whispering, "Are you paying attention?" And someone was. Someone noticed. And that quiet attention, it's about to guide us somewhere much stranger than we thought. While the muon was drifting off course in Illinois, something just as unsettling was happening far away, under the mountains near Geneva, Switzerland. And it matters that we talk about these things together, gently, side by side. Because when two completely independent anomalies from 2 different experiments, studying 2 different kinds of particles, both start pointing in the same direction, well, that's not something you can brush off as coincidence. The Large Hadron Collider Beauty Experiment, LHCb, was built for a very specific purpose. While other detectors at CERN look for new particles by smashing protons together as hard as they can and watching what bursts out, LHCb takes a softer, more careful approach. It studies the behavior of particles called bemesons, particles that contain what physicists call a beauty quark, or a bottom quark. Just breathe with it for a moment. It's a lot, I know. But we're here, taking it one step at a time. These particles, they're heavy, and they're unstable, and they only live for about 1/trillionth of a second before they quietly fall apart into lighter ones. And the reason we study them so closely is because the way they decay can be incredibly sensitive to new physics, to things we haven't discovered yet. Even the tiniest nudge from some unknown force or particle, it can shift their decay in ways we can actually measure. It's a gentler approach to finding something new. Instead of trying to spot new particles outright, you watch the familiar ones and you look for little hints, little signs that something unseen is shaping their behavior from the shadows. The Standard Model gives a very clear, very precise prediction about how beamosons should decay. And one of the most important pieces of that prediction is something called lepton universality. Leptons are particles like electrons and muons, light, quiet particles that don't feel the strong nuclear force. And the Standard Model says, with a lot of mathematical confidence, that the weak force should treat electrons and muons exactly the same once you account for their difference in mass. That idea, lepton universality, it isn't just a guess. It comes from deep, elegant symmetries built right into the foundation of the theory. And that's why studying these tiny decays so carefully matters so much. What this means, in practice, is really simple and kind of beautiful. If you make a beamoson and let it decay, the chances that it gives you an electron or a muon, they're supposed to be the same. Perfectly equal. No favorites. The universe, at least in the Standard Model, treats those two particles with this quiet, democratic symmetry. But when the folks at LHCb watched those beamosons decay, things weren't equal. Not quite. The ratio of muons to electrons kept coming in lower than expected. Not dramatically so, nothing that would make a casual observer gasp, but gently, steadily, the numbers drifted away from where they should have been. And as more data came in, that soft little deviation grew into something that made physicists pause, look at each other, and whisper, "We need to talk about this." In some decay channels, the difference was about 15%. I know, 15% sounds small, but in a theory that expects exact equality, a theory tested again and again across decades, 15% is a canyon. It means something out there was nudging those beamosons, making them less likely to become muons than they should have been, or more likely to become electrons. Either way, something was quietly tilting the odds. It's okay. Take another breath. We're just trying to understand what the universe is trying to tell us. Imagine you're holding a perfectly fair coin in your hand and you flip it 1,000 times. And somehow, you only get 425 heads. It's unusual, sure, but maybe it's just bad luck. Now, flip it 10,000 times and that little ratio stays right there at 42% instead of 50. And then, 100,000 times, and it still won't budge. At some point, you stop whispering bad luck, and you start gently admitting to yourself, this coin is biased. And that's kind of what was happening with these beamoson decays. The universe, it was acting like it had a quiet preference, like it found muons just a little less interesting than electrons. Like something was softly nudging the decay paths away from the heavier lepton. And you can almost hear yourself asking, what could possibly make that happen? Because the Standard Model, it just doesn't have a place for that. Lepton universality isn't a suggestion there. It's a deep, fundamental symmetry. And if the universe is breaking it, then something else is touching these particles. Something the theory doesn't see. And the things theorists started whispering about were the same kinds of new, heavy particles that might also explain the muon's strange magnetic moment, maybe even carriers of a fifth force, things that care more about muons than electrons. And the really important part, the part where it starts to feel quietly unreal, is that these two mysteries were completely separate. The muon Go 2 experiment at Fermilab was measuring something entirely different. Both anomalies, they involved muons specifically. And it's okay, just take a moment with that. The muon was the quiet little thread running through everything. And in physics, when two measurements that shouldn't have anything to do with each other both point to the same particle, that's when people start to lean in. That's when coincidence starts to feel like something that needs explaining, not something you just accept. And the idea that began to form, gently, slowly, was this. What if there's a force that pays special attention to muons? Not a force that treats all matter the same, like gravity. Not one that touches every charged particle, like electromagnetism. But something softer, stranger. A force that cares only about this one kind of particle. Something that nudges a muon's spin in a magnetic field and quietly discourages certain decay processes involving muons. Something that, for reasons buried deep in its own nature, simply ignores electrons, quarks, protons, everything else we're made of. For a little while, it felt like the universe was playing favorites. And what that might mean, what it might be gently pointing us toward, that's where our story goes next. At some point in science, you reach this gentle threshold where the evidence isn't quite strong enough to confirm a theory, but it is strong enough to give it a name. And that threshold had been crossed. Physicists began writing papers, hundreds of them, softly searching for what kind of new physics could explain both the muon's strange magnetic moment and the hints of lepton universality breaking down in Bemeson decays. And the name that kept coming up, whispered again and again, was a fifth fundamental force. To understand what that really means, let's take a calm moment and revisit how forces work in the quantum picture of reality. We feel forces as gentle pushes and pulls, gravity drawing you toward the Earth, magnetism guiding a compass needle, the nuclear forces holding atoms together where our eyes can't follow. But in quantum field theory, forces aren't passed along by touch or by some mysterious distant influence. They're carried by particles, quiet little messengers called bosons. The electromagnetic force is carried by photons. Yes, the very same particles that make up light. Every time two charged particles interact, they're exchanging these tiny virtual photons, fleeting, too brief to ever see directly, but real enough to carry energy and momentum between them. Just breathe. It all fits together more gently than it first seems. Take your time with this, okay? Just breathe with me for a moment. So, the weak nuclear force, the one that guides certain kinds of radioactive decay, it's carried by these heavy particles called the W and Z bosons. They were discovered back in 1983 at CERN, a really beautiful milestone in physics. And the strong force, the one that keeps quarks held safely inside protons and neutrons, that one is carried by particles we call gluons. Every force has something that carries it. And if there's a fifth force out there, it would need a carrier too. The one people talk about the most, especially when we think about something that might act only on muons, is called the Z' boson. The name echoes the Z boson on purpose, because it would sort of play the same kind of role, gently mediating interactions between particles. But unlike the Z boson, which treats all fermions more or less the same, the Z' would be very particular. It would reach out strongly to muons and barely touch electrons, or the quarks inside protons and neutrons. And that's okay. There's no rule saying a force has to treat every particle equally. The ones we already know don't do that. The strong force, for example, doesn't affect electrons at all. What makes the Z prime feel so unusual isn't the selectivity. It's that its selectivity would match the strange little anomalies we've been noticing. And still, no detector has seen it directly. That means, if it's real, it must be either heavy enough or quiet enough in its interactions that it's slipped past every search so far. It's a lot, I know. Another popular candidate is the leptoquark. It's a hypothetical particle, something the standard model doesn't quite know how to hold. It carries both lepton number and baryon number at the same time, which is unusual and kind of beautiful in its own quiet way. It means it can touch both leptons and quarks in a single interaction, bringing them together where normally they stay apart. A leptoquark could gently mediate the beam-meson decay LHCb was watching, turning a bottom quark into a strange quark, while softly shifting the balance between muons and electrons in the final state. These particles show up in theories that stretch beyond the standard model, even in some grand unified ideas. And people have looked for them at CERN, really looked, and found nothing yet, which just means that if they're out there, they're either very, very heavy, or their connection to the particles we can study is incredibly faint. And what's interesting is that both of these possibilities, the Z prime and the leptoquark, share something that, with just a touch of drama, you might call elitism. They wouldn't interact with everything equally. They'd choose. They'd prefer, especially muons over electrons. And that quiet, selective behavior, that's what makes the fifth force idea feel truly different from simply adding one more particle to the standard model. It's okay. Just take a breath with it. This is a lot, but you're doing fine. Think of it gently. It suggests a force shaped by a different set of rules, something softer, quieter, almost out of reach. A whole other layer of interaction, that ordinary matter, that you are almost completely untouched by. Breathe with that idea for a second. The forces you feel every day, the electromagnetic pull that keeps your cells together, that holds electrons close to their nuclei, that lets chemical reactions happen, that lets light carry the world into your eyes, all of that happens because you're made of charged particles. You have charge, you have mass, you have the quantum pieces needed to connect with those forces. But this fifth force, in this picture, it would need something different. A quantum property ordinary matter barely has, or maybe doesn't have at all. It's like a radio station broadcasting softly, steadily, but your receiver just isn't built to tune into it. The signal could be everywhere around you, gentle, constant, and you'd never quite feel it. Just imagine it for a moment. This force, quietly moving through you, passing through the chair beneath you, through the walls around you, down into the rock beneath the building, and you wouldn't feel a thing. Not a vibration, not a warmth, not even the faintest whisper. Nothing at all. And this is where things begin to shift gently into something a little more existential. Because this idea of a fifth force, it isn't just about two strange signals in particle detectors. It's about what those signals might be reaching toward. If there is a force that chooses to interact only with muons and simply drifts past ordinary matter without a care, then we have to wonder, softly, what else it might be touching. What else it might be meant for, if we can even use that word. Maybe it's tuned to something we can't see. Something that, in sheer amount, quietly overwhelms everything we've ever observed. And the answer theorists kept returning to, the one that made this whole idea feel so unsettling was dark matter. And to understand why that connection feels so important, so heavy in its quiet way, we have to talk about just how much we still don't know. Imagine the entire electromagnetic spectrum, from radio waves longer than a football field to tiny gamma rays smaller than an atomic nucleus, as all the ways reality can speak to itself. All the channels, all the frequencies. Just let that settle in. And now imagine that we, made of atoms and held together by the four forces we know, are tuned to only a tiny sliver of that spectrum. It's okay if that feels big. Just breathe. We can see visible light. We can build tools to sense radio waves, X-rays, infrared. We can even feel the gentle tremors of gravitational waves, ripples in space-time itself, discovered in 2015, and still so much more astonishing than we tend to remember. Our instruments stretch our senses far beyond what we were born with, but still, we're held by the limits of the forces that shape us. It's all right. Take your time. With that, you don't have to rush. What we can detect, it's only what touches us, what reaches the channels we're built to hear. And that's okay. But imagine, gently, like a quiet thought drifting in, that there are other channels out there. Not electromagnetic ones, those are already mapped. Something softer, stranger. Force channels, interaction channels. Ways of communicating through quantum properties we simply don't have. Picture tiny particles moving through a room, information whispering across the universe, structures forming and fading, all through a kind of charge we were never made to feel. And here we are, made from particles tuned to just 4 forces, sitting inside this whole transmission without even knowing it. Like an AM radio in a room full of FM signals, hearing nothing but silence. And this isn't science fiction. It's a gentle, serious way of thinking about what a 5th force could mean, if it's real. Sometimes the reason we can't detect something isn't that our tools are weak. It's just that we were never built to hear it. And that's okay. Sometimes it's just that our instruments are made from the wrong things, you know? And sometimes it's that whatever we're trying to detect is touching a part of reality our tools just can't feel, because they're not built from the stuff that could feel it. And it's okay to sit with that. It's not a failure of technology. It's something deeper, something structural. And that difference, it really matters. Especially when we're trying to understand these 5th force anomalies. It brings up a question that's both scientific and a little philosophical. How do you tell the difference between a signal you simply can't detect and a signal that was never there at all? Just breathe with that for a moment. And when we think about the muon anomaly and the lepton universality violation at LHCb, become gentle little reminders of how strange and special the muon really is. It's not ordinary matter in the way a proton or an electron is. It's brief, exotic, appearing only in high-energy collisions or when cosmic rays brush the upper atmosphere. And still, it behaves differently from electrons in these subtle ways we don't fully understand yet. It's okay. We're still learning. What I'm about to share might feel a little strange, but that's okay. So, if there really is a 5th force, one that whispers to muons but stays completely silent to electrons, then the muon isn't just a heavier cousin. It's something in between. A quiet little bridge. A particle that lives mostly in our world, but has one foot, just barely, resting in another place entirely. A particle that can hear a transmission the rest of ordinary matter is totally deaf to. And That's why both of these anomalies keep coming back to the muon. That's why people got excited, not just because 2 experiments agreed, but because that agreement pointed at the muon as something uniquely tuned, like it was listening to 2 frequencies at once. But hey, listen, there's a difficult part here too, and it's okay to sit with that. If this 5th force is so faint, so gentle, that we only see it through the tiny ways it nudges muons, then confirming it becomes really, really hard. Everything we find will be indirect. Every measurement will be an echo, not the interaction itself, just the soft impression it leaves behind. And echoes can fool us. In physics, just like in life, the room you think you're hearing might not be the room that actually made the sound. It's all right. Just take your time with that. I'm right here. Is what we found a genuine signal from another frequency of reality? Or have we just been sitting in a very quiet room, hearing our own blood pressure and calling it music? It's okay to ask that, even if it feels uncomfortable, because that question really is at the heart of this whole story. And to understand how much rests on the answer, we need to take a gentle look at what the signal might be telling us about the hidden majority of everything that exists. There's a number in cosmology that should bother you, more than it probably does. All the ordinary matter, the protons, neutrons, electrons, the photons, everything you've ever seen, touched, measured, or built an instrument to detect, it's only about 5% of the total energy in the universe. Just 5%. Everything, every star, every planet, every atom, every galaxy, every person who has ever lived, every instrument ever built, every measurement ever taken. 5%. And the rest, the remaining 95%, it's made of things we can't directly detect. About 27% is dark matter. It has mass, it has gravity, but it doesn't interact with light. It can't emit it, absorb it, or reflect it. And the final 68%, that's dark energy. Something even more mysterious. Something that seems to be pushing space itself to expand faster and faster. Take a breath. It's a lot, but you're okay. We're just exploring it together. We know dark matter exists for a few important reasons, and it's okay if it feels a little confusing at first. Just take a breath. The simplest and oldest clue comes from how galaxies rotate. When astronomers look at the stars way out at the edges of a spiral galaxy, they find them moving much faster than they should. In a calm, normal spread of mass, gathered mostly toward the center, the way we see with the stars and gas we can actually observe, those outer regions should slow down. That's just gentle, familiar Newtonian gravity at work. It's the same reason the outer planets in our solar system drift around the sun more slowly than the inner ones. That's how it's supposed to be. But the outer edges of galaxies, they don't slow down. They keep moving at almost the same speed as the stars near the center. And that quiet, persistent mismatch is one of the soft, steady ways the universe tells us dark matter is really there. The only explanation that really makes sense is that there's this massive, invisible halo of matter gently surrounding, even stretching far beyond, the visible galaxy. Matter that pulls on everything with its gravity, but never lets us see even the faintest glimmer of light. And the thing is, the amount of this missing mass isn't small. Not at all. It's about 5 to 6 times the mass of all the visible matter in the galaxy put together. So, we've established that dark matter is real, that there's vastly more of it than the matter we can see, that it has mass. What we don't know is what it's made of. And, maybe most importantly, we don't know whether it interacts with ordinary matter through anything other than gravity. For decades, people assumed it didn't. That dark matter was quiet, untouchable, only tugging through gravity, but completely separate from everything else that shapes our world. Scientists have built experiment after experiment deep underground, trying to catch even the faintest hint of a dark matter particle. Tanks of liquid xenon, delicate germanium crystals, spheres of liquid argon, and still, nothing conclusive. Dark matter, whatever it is, has been incredibly good at hiding. And now, here's where things start to connect, where the idea of a fifth force becomes something more than just a curiosity from a couple of particle physics results. If a fifth force exists, one that touches muons, one that leaves ordinary electrons and quarks alone, one carried by some new boson we haven't yet seen, then a gentle but important question naturally rises. What else might this force reach out to? So, the answer they keep coming back to, the one that fits so neatly into all those models trying to make sense of these strange little anomalies, it's dark matter. I know it sounds big, but stay with me. There's this idea that something like a Z-prime boson, or maybe a leptoquark, or some other gentle little carrier particle could reach out and touch both sides at once, the muon world we can see and the dark matter world we can't. It's like a bridge. Not gravity. Gravity already ties everything together in its own quiet way. This would be different. Softer, more intentional, a new kind of connection, a non-gravitational thread between the tiny bit of the universe we know and the vast invisible part we're still trying to understand. This is why these little anomalies, if they're real, they matter so much more than just the world of particle physics. Take a breath with me for a moment, because if this fifth force is really a bridge to dark matter, then those tiny statistical whispers in a magnetic ring in Illinois and a detector tucked quietly under the Swiss mountains, they might be the very first time in all of human history that we touched something from the dark sector in a way that wasn't just gravity. The first time that vast hidden majority reached out gently and brushed ordinary matter on the shoulder. And we almost noticed. Let me be really clear about where we are now. This part, it's informed speculation. It's okay to sit with that. Theoretical physics is full of ideas that aren't confirmed yet, that might never be. But they grow naturally from things we already trust. And when some of those ideas are laid out, slowly, carefully, they show us just how much we might be missing. So let me walk you through a few of them, softly, step by step, with the understanding that we're in the space of theory now, not measurement. The way we usually think about dark matter, it's so simple, almost featureless, like tiny points just gathering quietly under gravity and nothing more. But it could be so much richer than that. If dark matter carries its own soft, hidden force, its own kind of electromagnetism, moved along by what theorists call a dark photon, then dark matter might interact with itself in ways we've never seen. It could form dark atoms, dark molecules, even release and absorb its own kind of light, a quiet, invisible glow we could never detect, because it touches only dark charge, not the ordinary charge we know. And maybe, in a truly astonishing possibility, it could gather into dark stars, places where dark matter presses in on itself and radiates in ways we simply can't perceive. And it's okay to remember, there's no evidence for any of this yet. None of these things have ever been seen, because if they shine only in dark light, nothing we build from ordinary matter can catch them. But whether these ideas are true or not, it all gently circles back to our bigger question. Because the answer depends on whether the little hints from Fermilab and CERN are real. If they are real, if this fifth force truly exists, gently touching both muons and dark matter, then the dark sector isn't just some distant cloud of drifting dust. It becomes a world of its own, invisible, inaccessible, but still real. A quiet place with its own physics, its own chemistry, its own structures, passing through us all the time, overlapping our space, sharing our gravity, even if we can't ever quite reach it. And if these little anomalies are just noise, then all of that fades away again, slipping back into speculation with nothing solid to hold on to. That's the fragile moment we're standing in. Everything here rests on a signal that hasn't yet been confirmed. And that's exactly why the tools we built, the ones meant to help us find the truth, matter so much. There is a building, 27 kilometers in circumference, buried quietly beneath the French and Swiss countryside near Geneva. Just take a moment with that. If you were to get in a car and drive at a calm, steady highway speed along the tunnel that holds this machine, it would take you about 16 minutes just to finish one gentle lap. And this tunnel, it rests between 50 and 175 meters underground, tucked into layers of rock and clay that once formed the floor of a shallow ancient ocean, millions and millions of years ago. Just imagine that. It's okay if it feels big. It is big. $10 billion. A decade of careful construction. Thousands of engineers, physicists, and technicians, all from over 100 countries, all coming together for this one machine. And when it was finally finished, from the surface, it didn't look like much at all. Just a few quiet, unremarkable buildings scattered across peaceful fields on the outskirts of Geneva, connected by access shafts to something extraordinary, happening far beneath your feet. It's okay to let that settle in. You don't have to rush. The Large Hadron Collider, it's cooled all the way down to 1.9 Kelvin. I know that's just 1.9 degrees above absolute zero, that place where all molecular motion would simply stop. It's okay if that sounds overwhelming. We can go slowly. Out in the emptiness of space, far from any stars, warmed only a little by the leftover glow of the Big Bang, the average temperature is about 2.7 Kelvin. So the LHC, it's even colder than that quiet background of the universe. It's colder than the surface of Pluto, sitting way out there at around 44 Kelvin. It's colder than almost anything that naturally exists in the whole observable cosmos. Just let that settle in for a moment. And getting it that cold, keeping it that cold, it takes so much care. About 10,000 tons of liquid nitrogen just to pre-cool it. Then over 120 tons of superfluid liquid helium flowing gently through a plumbing system that wraps all the way around the ring. It's a lot, I know. But it's all essential. Because those superconducting magnets, the ones that guide the proton beams, they only become superconducting, only carry current with zero resistance when they're brought this close to absolute zero. It's okay. You don't have to rush through the idea. If they warm even a little in the wrong spot, they lose their superconductivity right away, and all that magnetic energy rushes out in a sudden, violent burst. I know that sounds scary. The LHC has gone through that before, and it's really not a pleasant thing. Inside this frozen ring, it's all right. Just imagine it gently. Protons are being guided through smaller machines, one step at a time, before they're finally eased into the main collider. There they drift in two beams, moving in opposite directions, almost touching the speed of light. 99.9999999% of it. And that's okay. At those speeds, things begin to feel different, in ways that matter. Time itself seems to shift for them, compared to the engineers watching from above. Their mass, at least from our perspective, grows so much, and that energy is what makes the collisions meaningful. The magnets that keep these beams on track, they have to be incredibly strong, about 100,000 times stronger than Earth's own magnetic field, just to gently hold the beams in place, keep them circling, instead of flying off in straight lines. There are about 9,600 superconducting magnets arranged all around the ring, each one with its own role. Dipole magnets to bend, quadrupole magnets to focus, others to make tiny adjustments. Every single one is a delicate, precise instrument. Every one carefully tested. Every one cooled to that extraordinary temperature and held there, steady and calm, throughout the whole operation. And when those two beams finally meet, when the collisions happen, the energy released is, in everyday terms, so small. About the same as a mosquito in flight. It's okay to let that sink in. Because that tiny bit of energy is packed into a space smaller than an atomic nucleus, a place so small the comparison almost feels unreal. It's like taking hey, it's all right, just take a moment with me. So, at that concentration, the energy density reaches a place the universe hasn't felt since about 1/1,000,000,000th of a second after the Big Bang. I know that sounds huge, but stay with me. Particles that haven't existed freely for 13.8 billion years, they just flicker back into being for the tiniest instant, then fade into other particles that the detectors quietly catch. That's really the whole idea. Recreate a little piece of the early universe, just for a breath, and watch what appears. And LHCb, the detector we've been talking about, it's right there at one of those collision points. It isn't like the big spherical detectors, Atlas or CMS. No, LHCb is gentler, more focused, a forward spectrometer, almost like a set of calm, flat panels stretched along one side of the beam. That shape, it's because the beamisons tend to rush forward, and LHCb is tuned so carefully to follow them, trace their paths, and piece together their decays with incredible precision. For Run 3, starting in 2022, they rebuilt it, almost entirely. Even the trigger system, the part that decides, moment by moment, what to keep and what to let go, it's now completely software-based. And it handles about 1 terabyte of data every second. 1 terabyte every single second. Just breathe with that for a moment. All of that information is processed by a computing farm in a room about the size of a small warehouse, running machine learning algorithms trained on millions of simulated events, evaluating every single proton collision as it happens. Of the roughly 30 million collisions happening every second at the LHCb interaction point, hey, it's all right, just take a moment with me. Only the ones with signs of heavy quark decays, rare processes, or maybe even hints of new physics make it through the filter. The rest, the overwhelming majority, they're let go in real time, gone forever. And that's okay. The collision energy in Run 3, it was gently raised from 13 to 13.6 tera-electron volts. And that higher luminosity, it just means those rare processes gather in the dataset a little faster, like tiny moments adding up. LHCb in Run 3 is expected to collect more data in just a few years than in all the time before. And that's something to breathe into. And yet, even with all of this, with the most energetic proton collisions we've ever managed here on Earth, with detectors rebuilt to a sensitivity we never thought we'd reach, with data processing power that would have felt like pure science fiction to the physicists who dreamed up the first machine, we still haven't directly detected the new particles that the fifth force hypothesis needs. And that's all right. Take a breath. We're still searching. We're still here. Hey, it's all right. Just breathe with me for a moment. So far, no Z' boson has shown up in the collision debris, and no leptoquark has been traced in the particle tracks. I know that can feel disappointing. Those little hints we all got excited about, The wobbling muon, the strange decay ratios, they were real in the statistics, they really were. But the clean, direct signs we were hoping for, the kind of unmistakable peak that tells us a new particle has arrived, those just haven't appeared. And that puts us in a strange, honest place. There are really only two ways to look at it, and neither one sits perfectly. One is that the fifth force is real, but the new particles are simply too heavy for the LHC to make right now, or they interact so faintly that we just can't see them yet. Other possibility, and I know it takes a little courage to sit with, is that maybe those particles don't exist. Maybe the anomalies were just fluctuations. Maybe the fifth force isn't there at all, and the standard model, worn down but still standing, was right the whole time. And the machine we built, the most powerful one ever made, to look into the heart of reality, it hasn't told us which story is true. Not yet. That uncertainty, that pause, it's strangely honest, in its own way. Science has a whole language for uncertainty, and I want you to know it matters. It shapes everything about how this fifth force story has unfolded. Without that understanding, the headlines feel confusing, and the truth underneath feels even more so. It's okay. Take your time with it. I'm right here. Hey, let's take this slow, all right? When physicists share a result, they gently place something beside it called the sigma level. Just think of sigma as a soft little measure of how sure they are, how likely it is that what they saw is real, not just a random flicker in the data. 1 sigma? That means there's about a 32% chance it's just a fluke. I know. That's almost 1 in 3. You wouldn't stake your career on that. Honestly, you wouldn't even stake your lunch on it. And that's okay. 2 sigma? That's roughly 5%. Better, sure, but still 1 in 20. Still well within the kind of things that just fade away the moment you gather more information. It happens. And then there's 3 sigma. The field gently calls that evidence, with a lot of caution built right into the word. At 3 sigma, there's about a 0.3% chance it's a fluke. That sounds small, and it is. But particle physics has been hurt before by 3 sigma results. Enough times that everyone treats them more like interesting hints than firm conclusions. It's all right. We're just taking our time with it. 5 sigma, it's a kind of certainty, you know? Just take a breath with me for a moment. It means the chance that what you're seeing is just a random fluctuation is less than 1 in 3.5 million. Imagine that. It's like needing to flip a fair coin and have it land heads 22 times in a row. Not impossible, just so unlikely. And that's why, at 5 sigma, the physics community feels safe enough to say, gently but confidently, yes, this is real. They've learned through hard experience when the risk of being fooled is finally small enough. And there's something quietly beautiful in the way particle physics protects itself and its people from wishful thinking. It's called blinded analysis. Just take your time with that idea. Before an experiment shares a new result, data, it's deliberately hidden in a careful, technical way. The teams can't see the true number they're measuring, whether the anomaly is big or small, whether it's even there at all. Not until everything in their analysis is fully decided and written down. They choose ahead of time exactly how they'll treat the raw data, which events they'll include, which systematic effects they'll account for, all before they let themselves look. It's a way of gently guiding human expectations, keeping the evidence clean, and reminding ourselves that wanting something to be true doesn't make it so. Hey, just take a breath with me for a moment. So, the effects they'll correct for, and how much the way their statistical method will work, even how they'll handle those little edge cases, all of that is decided gently and carefully, long before anything else happens. It's written down, settled and kept still, almost like it's being held softly in place. And only then, only when the whole analysis pipeline is sealed tight against any change, do they lift the blind. The number appears. Whatever it is, that's what the analysis gives. There's no way to nudge it, no way to push it somewhere more comfortable. It just is. And that's okay. It's simply the truth of the process. Steady and unaltered. It's okay. Just take a moment with me. This isn't about paranoia, and it isn't about trying to guard against someone being dishonest. The people working on these experiments, they're so careful, so committed to finding the real answer. They want the truth, not just the result they hope for. And blinding, it's really just a gentle protection against something quieter. Something we all feel, motivated reasoning. Our minds are powerful, always searching for patterns, always leaning on what we already believe. When you've spent years on an experiment, when you have an idea of what you think the outcome should be, your brain can nudge you without you even noticing, without your permission. Little choices, little interpretations. They can shift depending on whether they move things toward or away from what you expect. It's okay. Just breathe. Understanding this doesn't mean anyone's doing anything wrong. It just means we're human. Hey, it's all right. Just breathe for a moment. I know this has been years in the making. All those late nights, all those quiet arguments in your head and out loud, all that time spent thinking about this one thing, even when you were supposed to be somewhere else in your mind. And now the blind lifts, and it's extraordinary. Let yourself feel that. Someone types a command, and suddenly the number appears on the screen. And in that soft, fragile instant, the universe gives you its answer. Not anyone else's, just its own. Coming gently through your equipment, through your analysis, final and unchanging. It's okay to take that in slowly. You've earned that moment. You're not alone. Physicists describe the room in those moments as very quiet. The kind of quiet that feels like it has weight to it. Just take a breath with that for a second. The anomalies we've been talking about, they were real in the sense that they made it through the whole process. The Muon-G2 result from Fermilab was blinded, the analysis was done, and when the blind was finally lifted, the number that appeared was higher than what the standard model predicted. And the LHCb lepton universality measurements, they went through that same careful process over and over with different data sets. Each time the blind was lifted, and each time the number that came out drifted away from what the standard model said it should be. These weren't things someone just imagined or hoped into existence. They showed up because a carefully controlled, pre-committed analysis brought them into the light. And that is evidence. Not the final word, not a discovery, but real, steady, methodologically sound evidence that something in the data wasn't lining up with the prediction. It's okay to sit with that. Just breathe. Let me tell you about a different kind of plot twist. Gently, slowly. Not the kind that bursts onto the scene with discoveries confirmed, textbooks rewritten, press conferences buzzing, and names spoken alongside the giants who changed physics forever. No, this one is quieter, softer. The kind where the ground shifts beneath the measurement itself, almost without a sound. It isn't dramatic. It isn't because someone made a mistake. It's because the theory we trusted, the one the experiment was compared against, turned out to be less certain than anyone realized. And that's okay. Really, it is. To understand what happened, You just need to breathe and take in one simple thing about the muon G2 calculation that so much of the coverage rushed past. The standard model's prediction for the muon's anomalous magnetic moment, it isn't one clean number. It's a gentle sum of contributions from 3 different sectors of physics, each calculated in its own way, each with its own level of precision. Take your time with that. There's no rush. The first sector, it's quantum electrodynamics. Just take a moment with that. It's the gentle theory of how charged particles interact with light and with each other through the electromagnetic force. And the beautiful thing is, QED lets us calculate its predictions with extraordinary precision. You can trust it. It's steady. The second sector is the weak interaction. It's okay. It also adds a small, well-understood contribution to the muon's little wobble. These 2 parts, they're known so precisely that they aren't really a source of worry. They're solid ground. But the third sector, that's where things get a little harder. The strong interaction, the force holding quarks together inside protons and neutrons, it's governed by quantum chromodynamics. And it also nudges the muon's magnetic moment through something called hadronic vacuum polarization. Tiny virtual particles, quarks and gluons, they appear and disappear around the muon, giving its spin a little push, just like virtual photons and W bosons do. But unlike QED, QCD at these energy scales isn't something we can just work out cleanly. It's okay to acknowledge that. The math becomes what physicists call non-perturbative, meaning that the usual way of breaking the problem into smaller and smaller corrections just doesn't work here. The terms don't get smaller. The series doesn't settle down. You can't calculate this part the way you calculate everything else. And that's all right. Sometimes things are just harder to handle, and we take them one step at a time. For a long time, decades really, the hadronic contribution was handled gently through a kind of workaround. Instead of calculating it straight from quantum chromodynamics, physicists leaned on careful measurements of electron-positron collisions, moments where electrons and positrons quietly meet, annihilate, and give rise to hadronic particles we can observe. And from those observations, they inferred how much the hadrons would nudge the muon's little wobble. This approach, refined slowly, patiently, by many groups over many years, gave a number, and that number became the standard model's prediction. That's what the Fermilab measurement was being compared to when that strange anomaly appeared. And then, starting around 2021 and growing stronger through 2023 and 2024, another path emerged. A completely independent way of understanding that hadronic contribution. It's called lattice quantum chromodynamics. Instead of relying on experimental data, lattice QCD goes straight to the heart of the strong force, discretizing space-time into a gentle grid and solving the equations of quantum chromodynamics directly on it, using immense computing power. It's a quieter, more direct way of listening to the theory itself, and it began offering different answers. In principle, it's a gentler, more direct way of understanding things, a first principles calculation instead of an experimental inference. And when those lattice QCD results finally matured enough to be trusted, they quietly pointed to a higher value for the hadronic contribution than the experimental extraction had been giving. A value that, when folded into the full standard model prediction, brought the predicted muon anomalous magnetic moment a little closer to what Fermilab actually measured. Let me say that again, softly and clearly, because it really is the heart of the whole story. The muon didn't change. The Fermilab measurement didn't change. The muon is still wobbling at exactly the rate the experiment recorded. What changed was the number we were comparing it to. The theoretical target shifted. If the lattice QCD approach is right, then the standard model was always predicting something much closer to the measured value. And that apparent discrepancy, that 4 sigma anomaly that sparked years of excited papers about Z-prime bosons and leptoquarks and dark sectors, it wasn't a doorway to new physics. It was, at least in part, just the result of relying on an imperfect method to calculate something that's incredibly hard to get right. It's okay. Sometimes understanding simply takes time. Hey, it's all right. Just take a breath with me for a moment. You know, at certain points in that ongoing debate between those two theoretical camps, it almost felt like the distance between what we measured and what we predicted, it softened a little. It shrank from 4 sigma down to maybe 1? Or even less. And 1 sigma, in particle physics, it's nothing to be alarmed about. It's not a signal, not something shouting for your attention. It's just background noise, gently humming in the back. And that's okay. It's okay. Just take a breath with me for a moment. What I'm telling you, it isn't a scandal. No one fabricated anything. No one made some hidden mistake that should have been caught. For a long time, the experimental technique we had, it was the best we could use. And it gave results that were steady, consistent, and checked by many independent groups. And the lattice QCD work, it just wasn't ready yet. It needed years to grow, to develop, to gather the strength and precision it has now. Only then did it become something that could really challenge what we thought we knew. And at LHCb, things unfolded gently, but differently. As the new detector started giving us data at an incredible rate, the team released updated analyses. And with more statistics, the numbers began to shift. That ratio of muon to electron decays, the one that once seemed to drift away from the standard model's expectation, it slowly began to ease back toward 1. It's all right. Just breathe. Science takes its time, and sometimes the story changes as the picture becomes clearer. Hey, it's all right. Just breathe with me for a moment. These updates, the ones that came out in late 2022, they gently showed us something important. That key lepton universality measurement, it settled back into the standard model's uncertainty range, right where it could rest without strain. That 15-10% deviation everyone was so excited about, the hint that maybe the universe was secretly choosing between muons and electrons, it's gone now. Not just softened, gone. Just folded back into the statistical noise where maybe it had been waiting all along. And you know, someone described the LHCb result in a way that really stayed with people. They said the monster dissolved under light. Not with drama, not with any kind of roar. It just slowly lost its shape as things became clearer, until eventually, you couldn't point to anything and say with confidence that it had ever truly been there. It's okay. Let it settle. I'm right here with you. It's all right? Just take a moment with me. What makes this outcome truly interesting, not just disappointing, is what it gently shows us about the process, not the ending. The standard model, it held on again. For more than 50 years, it's met every real challenge, and each time it stayed standing, not because someone fought for it, but because we tested it carefully, patiently, and it was still right. Those little anomalies, they weren't ignored. They were treated with the seriousness they deserved, because that's the only honest way to face unexpected data. They were explored with the best tools we had. We followed them, step by step, until the data brought us clarity. And when that clarity came, it didn't just support the standard model. It reminded us that the way we test these things, the calm, careful method, is just as important. It's okay. Take a breath. We're just learning as we go. It's all right. Just breathe with me for a moment. The system worked, okay? And that isn't some small consolation prize. That is the whole point. Whether the ending feels triumphant or a little disappointing, that really depends on what you were hoping to find when you first started following this story. If you were hoping the fifth force would be real, yeah, this part might sting a bit. And that's all right. Just take your time with that feeling. But if what you wanted was to see science move the way it's meant to, gently, honestly, without clinging to the outcome we wish for, then this chapter is exactly the kind of quiet, steady proof you were looking for. It's okay. You're doing just fine. It's all right. Just take a moment with me. The fading of an anomaly, it isn't the same as a refutation. I know it sounds like something a scientist might say just to soften a disappointment, but no, it's not meant as comfort. It's a real, gentle, important truth about how we understand things, especially at the edges of what we know. When a signal weakens as the data gets better, it's confusing, I know. It doesn't fit neatly into winning or losing, success or failure. And that's okay. It really is. There are 3 different ways to interpret what's happening, and the honest thing, the kind thing, is to hold all 3 at once, not to cling to whichever feels safest or most dramatic. Just breathe. It's a subtle place to stand, but you don't have to rush. I'm right here with you. The second interpretation, it's a little more interesting, and it's much harder to brush aside. Just take a breath with me for a moment. The effect might really be there, just smaller than we first thought. The early data, with all its uncertainty, may have made it seem bigger than it truly is. And in this gentler version of things, the signal doesn't fade away to nothing as we gather more information. No, it's still there. A real part of the universe, settling slowly into its true, quieter value. It may not be as dramatic as those first hints made it seem, but it's still real. Still something. Still not zero. It's all right. Just take a breath with me for a moment. This interpretation, it can't be ruled out. Not completely. And that's okay. The updated LHCb results, they didn't measure leptin universality to be exactly 1 with absolute certainty. They simply found it to be consistent with 1, given the uncertainties we still have. Those uncertainties, they're smaller now, yes, but they're not gone. There's still a little space, a little room within those error bars, for a small but very real deviation. And remember, even a small signal, if it's real, is still a signal. If the true deviation from leptin universality is 5% instead of 15%, that still means something. It's still a violation of a fundamental symmetry in the standard model. It's still a quiet, gentle hint of physics that reaches beyond what we know right now. And that still deserves our attention. It still needs an explanation. Just breathe for a moment and let this settle in gently. The third interpretation, it sits a little differently from the others, you know? And if you follow it carefully, slowly, it changes the shape of the whole story. It's okay to take your time with that. The anomalies, they may really be pointing at something, but maybe not what the simplest versions of the fifth force idea suggested. Think about how physics unfolds, softly, patiently. The right theory, it's almost never the first one anyone proposes. When Uranus didn't follow Newton's predictions, people reached for all kinds of explanations, and most of them turned out to be wrong. And that's all right, because the truth, Neptune, it only came into focus after everything else had been gently ruled out. And the models people built for, the muon-Ge2 anomaly, or the LHCb lepton universality issue, those very specific Z-prime bosons, those precise leptoquarks, it's okay if those end up being wrong too. What really matters is something deeper, something quieter. The question of whether the underlying phenomenon they were trying to describe is real, that's a different question entirely. And it's okay to hold that question softly, without rushing. The broader context around this whole story, it's worth holding gently in your mind, okay? Because when you're focused on the path of just two little anomalies, it's so easy to lose sight of everything else. And it's all right. Just breathe. The Standard Model, for all its incredible power, is something we know isn't complete. It doesn't describe gravity, the force that keeps you grounded, the one that guides the planets in their calm, steady orbits. That whole part of our universe, it just isn't in the Standard Model's math. And that effort to bring quantum mechanics and general relativity together, to build a theory of quantum gravity, some of the brightest minds have spent a century trying. It's okay to let that feel big. There's still no confirmed answer. The Standard Model also doesn't tell us why our universe has more matter than antimatter. Why the Big Bang made just a tiny excess of particles over antiparticles. Why that little excess survived all that annihilation in the early universe. Why anything exists at all instead of nothing. Just take your time with it. It's a lot, but you're not alone. The broader context around this whole story, it's worth holding gently in your mind, okay? Because when you're focused on the path of just two little anomalies, it's so easy to lose sight of everything else. And it's all right. Just breathe. The Standard Model, for all its incredible power, is something we know isn't complete. It doesn't describe gravity, the force that keeps you grounded, the one that guides the planets in their calm, steady orbits. That whole part of our universe, it just isn't in the Standard Model's math. And that effort to bring quantum mechanics and general relativity together, to build a theory of quantum gravity, some of the brightest minds have spent a century trying. It's okay to let that feel big. There's still no confirmed answer. The Standard Model also doesn't tell us why our universe has more matter than antimatter. Why the Big Bang made just a tiny excess of particles over antiparticles. Why that little excess survived all that annihilation in the early universe. Why anything exists at all instead of nothing. Just take your time with it. It's a lot, but you're not alone. Just take a breath with me for a moment. It's all right. What I'm about to share isn't meant to discourage you, only to keep our expectations honest, gently and clearly. In particle physics, there's a long history of things that looked promising, but turned out not to be what we hoped. For example, the Dama experiment, tucked safely beneath Gran Sasso Mountain in Italy, has been saying for decades that it sees dark matter, a soft, steady yearly rhythm in its data, like a quiet seasonal heartbeat. And that signal is there, the modulation is real. But no other experiment anywhere else in the world, using different methods, has ever been able to confirm it. And that matters. And then there were the Atlas and CMS experiments at CERN. Back in 2015, they both saw something that made the whole field hold its breath. An intriguing little bump. Pairs of photons at about 750 giga-electron volts. It sparked this huge wave of excitement. Hundreds of papers, so many ideas, all trying to explain what it might be. New particles, new physics, extensions to what we thought we understood. But then, The 2016 data arrived. More information, a clearer picture. And that little excess, it was gone. Completely gone. And that's okay. It happens. It's part of how we learn, slowly and patiently, always moving forward. Just breathe. It's all part of the process. It's all right. Just take a moment with me. Breathe. What happened here, it was simply a statistical fluctuation, the kind that small sample mathematics tells us will show up from time to time. And that's okay. It doesn't mean anyone did bad science. It's not something to be ashamed of. It's just the universe behaving exactly the way the math says it should. And the lesson, it isn't to stop feeling excited when something strange appears, or to grow cynical when the unexpected shows up. It's more gentle than that. It's about learning to calibrate that excitement, to match it to the sigma level, to what similar signals have done before, to whether other experiments quietly, carefully, are seeing the same thing in their own way. Calibrated excitement doesn't take anything away from you. It's still excitement, just the kind that can survive contact with more data. We haven't found a fifth force, but we also haven't proven it doesn't exist. Those two things, they're not the same. And in the space between them, in that soft, uncertain gap between not knowing and not yet knowing, that's where the real work keeps going. Just breathe. It's okay. Here we are, finally arriving at the place this whole story has been gently guiding us toward. Not a conclusion, no, there isn't one, but more like a soft landing, a moment where all the threads settle together, not to form an answer, but to give us a clearer, calmer look at the question itself. And you, right now, you're made of something like 10 to the power of 28 atoms. I know that number is so huge it barely even feels real. It's less a number and more a reminder of just how small our human scale is compared to the vastness of the physical world. 10 to the 28th. If you tried to count each atom, one per second, without ever stopping, it would take longer than the universe has existed. Just let that sit with you for a moment. Each one of those atoms has a tiny nucleus with a soft cloud of electrons around it. Inside that nucleus are protons and neutrons, and even those are made of quarks, held together by the strong nuclear force. It's a lot, I know, but it's okay. Just breathe. You're doing fine. Every single one of those quarks, every single one of those electrons, they're all touched gently by the 4 fundamental forces. Just take a moment with that. The strong force, it quietly holds the nucleus together, keeping everything grounded. And the electromagnetic force, it's always there, guiding the chemistry in your cells, the soft electrical signals moving through your neurons, even the light that finds its way into your eyes. And then there's the weak force, shaping those subtle radioactive decays that make the sun's warm, steady energy possible. The energy that nurtures almost all life here on Earth. And gravity, it's the force that keeps you here, held safely on this planet. Just breathe. It's all connected, gently, steadily. And you're a part of it too. 4 forces. Just take a moment with that. Everything you've ever felt, everything you've ever touched, or seen or measured, all of it comes from those 4 forces and how they interact with the particles of the standard model. And that standard model, it only explains about 5% of the universe. I know that's a lot. It's okay to sit with it for a bit longer than it takes to read it. Not because it's something brand new, we've talked about these numbers before, but because of what it really means when you're inside that reality. Just breathe. Let it settle. It's all right. Hey, take a moment with me. Just breathe. So, the muon anomaly, the B-meson decay measurements, all those years of careful work at Fermilab and LHCb, they were really just gentle attempts, Reaching out from that tiny 5% we understand, trying to touch the other 95 we don't. Not with our hands, not with anything ordinary, but in the softest, most indirect ways we have, watching how a muon wobbles in a magnetic field, counting how often a quark chooses one path over another, looking for the faintest fingerprint of something invisible, hidden inside the things we can see. It's okay. Just let that idea settle. We're getting there, slowly. And we're not alone in the search. For a little while, it really felt like we were seeing something real, something gentle, something just barely pressing through, as if the boundary was thin enough for a mark to show. And for those few years, that was exciting. It was uncertain, but in a way that made you hold your breath just a little. But then, the numbers shifted. The data settled. The signal softened, like a whisper fading before you can quite catch the words. And the universe, with all its quiet, ancient patience, simply chose not to confirm what we thought we saw. It's okay, really. Sometimes the universe doesn't answer the way we hope. And that's hard, I know. But it's still there, steady and vast, whether we understand it or not. Just breathe. We're still here. Hey, let's slow down a bit together. Take a breath with me. Now, think about the Michelson-Morley experiment of 1887. It's okay. We can walk through it gently. Albert Michelson and Edward Morley, they were trying to measure the speed of light as it moved through something people then believed in, something called the luminiferous ether. It was supposed to fill all of space like a quiet, invisible medium that light waves could travel through, the same way sound moves through the air. And they built this incredibly delicate instrument, an interferometer, something so precise for its time that it could sense the tiniest shift in how long light took to travel if the Earth were drifting through that ether wind. But it didn't find anything. And that's okay. The speed of light stayed the same in every direction, no matter how the Earth moved. The ether, it just didn't seem to be there at all. Take another breath. You're doing fine. Hey. So, the result really confused and troubled the physics community for years. It felt like it shook something everyone thought they understood, something deeply held about how reality was supposed to work. And no one really knew what to do with it at first. But that quiet, empty-handed result, that careful measurement of something that simply wasn't there, that became the foundation Einstein used to build special relativity 18 years later. The very absence of the ether, measured so precisely, gently pointed us toward the truth that space and time weren't what anyone imagined. That negative result, in hindsight, it was the most important discovery of that whole era. Not a consolation prize. The real discovery. And we might be living through something a little like that again. Those fifth force anomalies, they may not have been what they looked like. The models we built to explain them might be wrong. But the way the anomaly appeared and then slowly faded, it's told us things we didn't know before. It's shown us that muons are uniquely sensitive probes of physics beyond the standard model, more sensitive, moment for moment, than almost any other particle we can actually work with. It's shown us that the theoretical calculation of the hadronic vacuum polarization was less understood than anyone realized. And it's shown us that LHCb, with everything it can do now, is going to keep giving us lepton universality measurements with a kind of statistical power we've never had before, for years to come. Just take that in gently. It's okay. We're learning more than we expected, even from what isn't there. It's all right. Just take a breath with me for a moment. And it has shown us something important, something clearer than what we had before. It's told us exactly where the edge of the standard model's confirmed truth sits right now. And finding that edge, even if it's a little farther away than we hoped, that's still progress. It's okay to feel a little disappointed. But physics doesn't stop just because an anomaly fades away. The questions that brought it to life, they don't disappear when the signal does. They just soften, shift, get guided toward better instruments, better ways of listening. So, gently now. What comes next in the search for that fifth force? For the non-gravitational face of dark matter? For that tiny crack in the standard model that we all know must exist because it can't be the final word? We keep going, one careful breath at a time. Hey, just take a moment with me. So, there are a few new experiments being developed, and some already running, that are looking at the muon's properties with even greater precision than the Fermilab Go-2 run. And that's okay. We can walk through it gently. The J-Park Muon Go-2 experiment in Japan, it's designed to measure the muon's anomalous magnetic moment too, but in a completely different way. A smaller ring, a different method of injecting the muons, and because of that, it comes with its own unique set of systematic effects. So if the Fermilab result had some tiny, subtle error that no one has spotted yet, J-Park wouldn't necessarily share that. And if both experiments end up agreeing, well, the confidence in the result grows so much stronger. Just breathe with that for a moment. And then there's the Mu2E experiment, also at Fermilab. It's looking for something even more dramatic than a small shift in the muon's magnetic moment. It's searching for a muon turning directly into an electron without producing neutrinos. Something the standard model basically says shouldn't happen at all. And if Mu2E actually sees it, that would be clear, unmistakable evidence of new physics. Not just a tiny deviation, but a forbidden process showing itself. And the sensitivity they're aiming for, if they reach their design goals, it would go about 4 orders of magnitude beyond any previous search. That's 10,000 times more sensitive. Just let that settle in. It's a lot. I know. But you're doing fine. At CERN, the Large Hadron Collider, it's quietly preparing for something big. Just take a moment with me. The upgrade to the high luminosity LHC, it's coming in the next few years, and it's going to gently raise the collision rate by about a factor of 5 to 7, compared to what we have now in Run 3. More collisions per second means more rare events, and more rare events, well, that means more statistical power to notice even the tiniest deviations from what the standard model predicts. The LHCb detector, already rebuilt for Run 3, will be getting even more care and attention. And ATLAS and CMS, they'll be significantly strengthened too. Altogether, through the 2030s, the HLE-LHC era will gather a dataset about 10 times larger than everything from Run 1, Run 2, and Run 3 combined. Just let that settle in for a moment. And if there really is a lepton universality violation, even at just a few percent, the HL-LHC will find it. If a Z-prime boson is out there, with a mass within reach of the LHC's energy, this era will gently but firmly reveal it, or rule it out from the most motivated mass range. The time of uncertainty, it's fading. And the time of clear, definitive answers, whether yes or no, it's drawing near. You don't have to rush. Just breathe. It's all unfolding. step by step. If a genuine lepton universality violation is really out there, even just at a few percent, it's okay. We'll find it in the HLE-LHC era. Just take a breath. If a Z-prime boson exists, and its mass is gentle enough to fall within the reach of the LHC's collision energy, the HLE-LHC will either uncover it or softly close the door on that most promising mass range. The time of statistical uncertainty, it's slowly coming to an end. And the time of clear, steady answers, yes or no, is quietly approaching. And when it comes to the search for dark matter, those direct detection efforts, those rare moments when a dark matter particle might nudge an ordinary atomic nucleus, they're still moving forward, step by careful step, toward deeper sensitivity. The Luxy Zeppelin experiment, resting safely in the Sanford Underground Research Facility in South Dakota, it's the most sensitive direct dark matter detector we have right now, holding 10 tons of liquid xenon with such calm purpose. Its sensitivity has already slipped beneath the theoretical floor set by the quiet, irreducible background of solar neutrinos. Just breathe. Science is getting us there. Just breathe for a moment. Let me walk you through this gently. The Darwin experiment, if it's ever funded and built, it would use 50 tons of liquid xenon, and it would reach sensitivities deep enough to touch the most carefully predicted dark matter models. And if dark matter interacts with ordinary matter through anything beyond gravity, even a quiet fifth force like the one we've been talking about, then experiments this sensitive might finally be able to see it. And out there in space, gravitational wave observatories are opening a whole new window for us. LIGO and Virgo have already heard the mergers of black holes and neutron stars, little whispers from the universe. And the LISA interferometer, planned for the 2030s, it's going to listen to things the ground can't hear at all. Supermassive black hole mergers, extreme mass ratio in spirals, maybe even echoes from the early universe itself. If dark matter shaped the birth of primordial black holes, or the phase transitions in those first moments after the Big Bang, then gravitational wave astronomy might carry soft traces of that role. Not the fifth force directly, no, but gentle hints pointing us toward a deeper understanding of the dark sector. It's a lot, I know, but it's okay. We're just taking it in together. It's all right. Take a slow breath with me. This debate, the one between the experimental extraction and the lattice QCD approach, it won't stay uncertain forever. Computing power is growing, gently but steadily. The lattice QCD methods, they're getting better, clearer, more reliable. And the systematic effects on both sides, they're being understood with more care than ever before. In the next few years, the uncertainty in the Standard Model's prediction for the muon's magnetic moment, it's going to shrink. Not all the way to zero, but enough that comparing it to the Fermilab measurement will finally feel clear, unambiguous. If the lattice QCD values settle into agreement with the measurement, then the anomaly softens, and the Standard Model holds steady once more, stronger and more carefully tested. But if the lattice QCD values and the experimental extractions keep disagreeing, and both still disagree with the measurement, then even the uncertainty becomes something we have to understand. And yes, it gets more complicated, but also more interesting. And if somehow, with better data and better theory working together, the measurement still stands apart from a well-understood Standard Model prediction, then we'll know we've stepped into new territory. And that's okay. We'll face that moment, gently, together. There's something gentle and honestly a little humbling here, and I think it deserves to be said softly, without trying to dress it up. Just breathe for a moment. Every scientific discovery we've ever made, every bit of understanding we've gathered about the world around us, from Aristotle watching objects fall to us catching the faint ripples of gravitational waves a billion light years away, all of it came from ordinary matter, touched only by the four forces we know. And it's okay to let that sink in. The whole structure of human knowledge, everything we've ever learned about physics, is just our attempt to describe 5% of what exists, written by tools and minds made from that same tiny 5%. Just take your time with that. It's a lot, but you're not alone with it. It's all right. Just take a moment with me. The other 95%, it isn't far away or absent from our lives. It's here, gently surrounding us, always present. Dark matter. It's passing through the room you're in right now, quietly, softly. Its gravity shapes the galaxy, guides the solar system to its place in the Milky Way, and helped create the conditions for Earth to form, for life to arise. And dark energy? It's the reason the universe keeps expanding, why galaxies drift farther apart, why everything has the vast structure it does. These things, they're not separate from us. They're part of the same universe we belong to, part of the quiet, immense context that made us possible. Just breathe and let that sink in. It's all right. Just take a breath with me for a moment. What those fifth force anomalies asked of the physicists, it wasn't the loud kind of bravery, not the kind that comes with bold claims or bright lights. It was something softer, quieter, a kind of courage that sits deep inside you. They had to follow evidence they wished would be real, follow it gently, carefully, honestly, even when it pulled them somewhere they didn't want to go. And then they had to accept where it led, even when it wasn't where they'd hoped. It's okay. That kind of courage, it's quiet, but it's real, and it matters. The physicists who worked on Muon-Gi 2, they really wanted that anomaly to be real. Just remember, they spent years of their lives on it, pouring so much care into every step. They moved a 50-foot magnetic ring across 1,000 miles of highway. Yeah, it was that important to them. They built these incredibly sophisticated analysis pipelines, checking and rechecking everything, gently making sure nothing was overlooked. And when the theoretical picture shifted, when those lattice QCD calculations started to challenge what they'd been comparing against, they didn't look away. They took a breath, engaged with it seriously, talked about it openly, and accepted that things were more uncertain than anyone had thought. And the physicists at LHCb, they wanted that lepton universality violation to be real too. It would have changed so much. But when the larger dataset came back, quietly lining up with the standard model, they didn't try to hide it or spin it. They just published it, honestly and clearly. It's okay to see all of this for what it is, people doing their best, even when the answers aren't what they hoped for. The wobble, it's okay. It turned out it may not have been what we thought it was. Just take a breath with me. The theoretical baseline shifted, gently, almost like it needed to. And the experimental confirmation at LHCb, it dissolved under better data, the way truth sometimes does when we look a little closer. I know everyone was hoping for a discovery, something big, something dazzling, but the story didn't end there. It ended, for now, with something quieter, something more honest, the precise edge of what we know, and a clearer sense of the tools and methods we'll need to keep going. It's okay. This is how progress feels sometimes: soft, patient, and real. We're still moving forward.
Oh, hey, sweetie! So good to see you! Okay, so listen, there's this whole big kind of intense theoretical debate going on about the hadronic vacuum polarization calculation. And guess what? It's still not settled. I know, right? One side is using experimental extraction, the other is doing lattice QCD, and they just keep giving totally different answers. And the cutest part, however that gets sorted out, is going to decide whether the whole muon anomaly sticks around or just disappears entirely. Wild! And oh my gosh, speaking of wild, LHCb is just collecting data like never before. Seriously, it's like they've turned into this unstoppable little data gathering machine. All those lepton universality measurements, they're going to get so much more precise because the stats are going to be way bigger than anything we've had before. And honestly, if there's a real violation hiding in there, even just a teeny tiny few % one, there is no way it can stay hidden with LHCb's new superpowered abilities. It's all going to come out eventually, and I cannot wait to see what happens next. Oh hey! So guess what? There are all these new experiments, Mu2e, the JPark muon G2, and this super exciting next generation of dark matter direct detection projects. And they're either already running or gearing up. How cool is that? And the high luminosity LHC? Oh my gosh, it's going to push those energy and luminosity frontiers way beyond what we got in Run 3. I know, right? So exciting. And get this, gravitational wave astronomy is opening up these totally new windows onto phenomena we couldn't even dream of seeing just 5 years ago. Isn't that wild? I love it. Now, about the fifth force, it might exist, it might not, and that's honestly part of the fun. Maybe those anomalies were like these tiny little fingerprints of something real that we just haven't learned how to read yet. Or maybe they were just noise playing dress up as signal. You know how noise can be when you're looking really hard and hoping really hard, and the statistics are just barely on the wrong side of the line. But oh my goodness, isn't the mystery delicious? Oh, hey there. So guess what? We actually don't know the answer yet, and that's totally okay. Isn't that kind of exciting? I mean, the fact that we get to just sit with that not knowing for a bit, keep working, keep measuring, keep tweaking things without rushing into some big dramatic conclusion. Oh, that's not weakness at all. That's real discipline, my friend. That's exactly the kind of patience that makes those amazing discoveries possible later on. And get this. Somewhere out there in that wild 95% we can't reach yet, there might be a signal, or a force, or maybe even a little bridge to something brand new. Something that's been passing right through your body every second of your life, through everyone who's ever lived, through the walls around you right this moment, down through the rock under your feet, and even across the space between galaxies, and we've never built anything that can catch it. Isn't that just incredible?
It's okay. Just let the idea settle for a moment. The openness of the question, that's the real discovery. Not a particle, not a force, not some confirmed signal from the dark sector. Just the gentle, honest truth that most of what exists is still beyond what we are. And it's all right. Take a breath. Because even knowing that, we still refuse to stop looking. We keep going anyway. And that's something quiet and beautiful. It's all right. Just take a moment. This is what the story is really about. Gently noticing the shape of what you don't yet know. That might be the most important knowledge you can hold. Because it shows you where to turn next, where to aim the instruments, where to look when the tools get better. It shows you the quiet corners where the universe has been keeping its secrets. And the signal, it might still be out there. Or maybe it isn't. but we're still listening. As carefully and as patiently as we can. Thank you for watching. Just take a moment with me. If this video moved you, maybe share it with someone who's ever looked up at the sky and quietly wondered what most of it is made of.